Okay, let's talk about this, and you'll see how it fits into today's lesson. So, one way to look at this, it says there's two numbers that we're looking for. So, one strategy would be to say, let's just call those two numbers x and y. If I can find x and I can find y, then I would find the two numbers that I'm looking for, right? You can call them n and m, it doesn't matter. But what this ends up being is what we call a system of linear equations. They give us some information. Now you can guess and check your way to this. Did anybody just guess at it and try some numbers and check it and maybe come up with an answer? Guess and check works sometimes. Maybe not super easy in this scenario. So the first thing it says is one number is 9 more than another number. So let's say x and y are our two numbers. Let's write an equation. One of the numbers is 9 more than the other number. Anybody want to throw out an equation for that? Go ahead, Luke.
I did x plus x minus 9, which would be 2x minus 9.
So you did x plus x minus 9?
Which would be 2x minus 9. Was what I got.
Oh, for your two numbers?
Well, my equation that I started with was 2x minus 9. And then what I did was, since it's a sum of...
So let me stop you. 2x, this, yeah, if I gather this together, this is 2x minus 9.
Then since it's a sum of two numbers, I multiplied that whole equation by 2. So then I got 4x minus 18. Then I solved for x. Then I took my x, which would be 7.
So what'd you get in the very end? What were your two numbers?
7 and negative 2.
7 and negative 2.
Which then you take 7 minus 2 is 5. 2 times 5 is 10.
Is that the correct answer? 7 and negative 2? Does that work? Yeah, the only thing I wasn't following you right here is you said 2x minus 9. I was waiting for you to say equals something. Like an actual equation. I'm gonna come back to that because I think you're correct. Equals 10. When you doubled it, it was equal to 10.
Yes.
Twice the sum of it was equal to 10.
Sorry.
Okay, so what you're saying is this is one of your numbers right here, and this is one of your numbers right here. Do you guys agree that one of those numbers is 9 more than the other number? Okay, so you went down a different path than I did because you defined both of them in terms of x, whereas I was defining one of them as x and one of them as y, which doesn't mean either one of us is more correct. You did two steps in one there, which I wasn't quite prepared for. What were you going to say, Mackenzie?
For the first equation, I did x plus 9 equals y.
Yeah, let's talk about that. So I'm gonna put Luke's off to the side. I think that was pretty good, Luke. Mackenzie says x plus 9 equals y. Does that give us an equation where one number is 9 larger than the other? I think so, doesn't it? Who's the larger guy? Y is larger. X is 9 smaller, but if I add 9 to x, then they would be the same, right? So one number is 9 larger than another. That's one equation. And then our second nugget of information said twice the sum of the two numbers is 10. Well, if my two numbers are these two guys right here, then the sum of those two guys would be x plus y, right? This is where Luke did x and x minus 9. And I'm going to get to that in a second, which is pretty clever. If I add x and y, and then I double it, I'm supposed to get what? 10, right? So notice here, this is what we call a system in two variables. We have a system of linear equations. We have two variables. We have both x and we have y, right? So if I were to take these two equations, if I were to say solve for y, if I take this first one and I get y all by himself, what would I need to do? Oh, I'm sorry, if I were to solve for x. Subtract 9 from both sides. So x is equal to y minus 9. So my 2 would be like y and y minus 9. Luke used x. Do you see where, are you guys following Luke's rationale? I didn't follow it right away, but it makes perfect sense. Okay? So there's a lot of different ways to do this. The idea is that we have 2 variables and we have to whittle it down into 1 variable. And if we can whittle it down into 1 variable, then we can solve the equation and then we can plug it back in, right? So I have 2 variables here. I'm just going to rewrite these guys. I'm going to say x plus 9 equals y. And then this guy here, 2x plus 2y, if I distribute, equals 10. So I got 2 equations. So we're going to talk about different ways to do this. And you guys have done this. You did it in 9th grade. You did it in 10th grade. But we're going to review this. One way to do this is to do what we call substitution. Where, how about I turn all of the variables into one of the equations, all into x's or all into y's. If I could get them all x's, or if I could get them all y's, then I could solve for the other one, right? So, for example, I already know that y is equal to x plus 9. So how about in my second equation, this is equation 1 and this is equation 2, how about in my second equation, every time I see a y, instead of writing y, I write x plus 9. That's what we call substitution, because they're the same thing. So anywhere I see a y, if I choose to write it as x plus 9, since we know y and x plus 9 are equal, I can do that, right? So if I rewrite this equation, everywhere I see a y, I'm going to write x plus 9. So I go 2x plus 2, here's a y, so I'm going to do x plus 9 equals 10. And now I just gather my like terms, 2x plus 18 equals 10. 4x plus 18 equals 10. 4x equals negative 8. And x equals negative 2. I just solved for one of my guys, right? Negative 2, notice what Luke had. He got negative 2 as one of his guys. Doesn't matter if it's x or y because we don't know which one was x or y before we started, right? And now that I know that one of my answers is negative 2, now I can use that knowledge to figure out my other answer, right? And I could just plug it back into one of these guys. That first one looks easiest. If x is negative 2 and I add 9 to that, y must be equal to 7. So how many of you got this? 7 and negative 2 before we ever started talking about this? Okay? So for those of you that didn't know how to do that, let's do a few more examples. I'm going to give you one to work on. And I'm going to specifically ask to see if you can do this by substitution. Meaning, try to do that same process that I just did. Where you try to take one of the equations and turn it all into x's. Or turn it all into y's. Doesn't matter which way you do it. And then try to solve that equation for whichever variable you did. And then once you solve for one of the variables, whether it's x or y, it doesn't matter, use that knowledge to solve for the other one. When you have both your x and y, Flag me down. Show me what you got. Was that a 5? That's a 3?
Yep.
Oh, I couldn't see it because you...
Yeah.
Good work. Anybody else? Very nice. Very nice. What do you got here? Yep, good. Okay, we're flying. No problem. Good. If you're stumped a little bit, ask your neighbor. What'd you guys get up here? What'd you get? Y is... Oh, you haven't gotten anything yet? Y is 3. Yep. Do you know X? The heavy lifting's done.
Yeah.
Once you find one of them, the other one should be really easy to find. So again, we're a system of linear equations. What'd you get? Nice. Good. Yep, we're going to do that in a second. Okay, I'm going to show you what I did here. Oops. I ended up getting 8 and 3 as my two answers. X was equal to 8. Y was equal to 3. So I asked you to do this, the substitution method. I know there's other ways to do this. We're going to look at a couple different ways to do this too. But if you were doing it the substitution method, the idea is to look at your two equations. If I call that equation number 1 and that equation number 2. One of the equations to me looks a little bit easier to isolate the x or the y. Like I could have isolated x or y in this guy, but then it's going to involve dividing by 2 or dividing by 5, and I'm going to get fractions, and that... Why deal with fractions if I don't have to deal with fractions, right? So I look at equation number 1, and I say, you know what, that one looks really easy to either get x or y by himself. All I got to do is move one of them to the other side of the equation, and I got what I want, right? So what I did is I just moved the x to the other side of the equation. I added x to both sides, and that's how I came up with this. So now that I know that y is equal to x minus 5, that's going to be my piece of information that I can use when I want to go to substitute. So now I'm going to go to my other equation, and I'm going to rewrite this equation, but instead of writing y, I'm going to substitute x minus 5. So this is about the simplest form of substitution that you can do in algebra, but you can see it's extremely handy when you're doing like more complicated equations and computation and whatnot. If you can take something complicated and substitute in something simple, when you know that they're the same thing, that really helps. So I'm going to rewrite now equation number 2. I rewrite it, but instead of writing a y, it's not 5 times y, it's 5 times x minus 5. And then I just do a little 8th grade algebra, and I find out that x is equal to 8. And like I was saying up front here, once you find one of your variables, the other one should be really easy. Like the hard work is done now. I know that x is equal to 8. Now I just go back to one of my two equations, and I plug 8 in for x, and I solve for y. And again, I'll just go to this equation because this is my simplest one. So I'll plug in 8, y equals 8 minus 5, therefore y is equal to 3. And we're home free. Okay? Let me share with you another method that we call the elimination or addition method. Go ahead and see if you know what I'm talking about on that guy right there. So we could substitute, but that's not what I'm asking you to do. If you wanted to substitute, probably move that 2y to the other side, and you would say x is equal to 2y plus 11, and then you'd insert the 2y plus 11 right there. I want you to try it with what we call the elimination or the addition method, where we're going to add the two equations together. We're going to add the x's, we're going to add the y's, we're going to add the constants in the hopes that one of the variables, either the x or the y, is going to cancel out. It's going to go to 0. Now, would that happen right now if I just added vertically? No. I'd get 4x minus 3y equals 0, and I just have another equation that's not going to do anything for me, right? So you might have to do a little algebra on one or both of the equations, before you do that addition method. Now I know all of you have seen this before. I guarantee it. If you haven't, your 9th, 10th, and 11th grade math teacher had no idea what they were doing. Because I guarantee you it is in every standard of every state and every algebra textbook that's ever been printed. It's just a matter of how much of this do I remember, and does it make sense to me, and can I work my way through it? What's that?
You should just make double best of.
Well, that wouldn't be challenging.
I know.
So a little bit about this idea of addition or the elimination method. Do you guys agree that if I have an equation, I'll call this one equation 1 and this one equation 2, off to the side, if you have two equations and you have a left-hand side is equal to a right-hand side, that's what an equation is, right? Left always equals right. That's why we use an equal sign in the middle. And then I have another equation, a separate equation, where a left is equal to a right. Okay? Does it make sense that if I add the two lefts together and I add the two rights together, that the two lefts are going to equal the two rights? Does that make sense? Intuitively, does that make sense? If something's equal to something and something else is equal to something else, if I take those two things and I add them together, wouldn't the sum of these equal the sum of these? Okay, that's essentially what we're doing, is we're taking the two left-hand sides of the equation. So the left-hand side is this guy and this guy. The right-hand side is this guy and this guy. Well, if I combine, if I add all of this together, and I add all of this together, then my left-hand side would still equal my right-hand side. But we just demonstrated that if I were to do that, if I were to go add these together, so I'm going to gather like terms. So I got a 3x and an x, that's a 4x. I got a 5y and a minus 2y, that gives me a positive 3y. And I got a negative 11 and a positive 11, that would give me a 0. I could go through and do that, and I could say that this is a true statement. The only problem is that doesn't get me anywhere. My whole goal is to try to whittle this down from two variables into one variable, and I haven't accomplished that because I came up with a new equation, but I still have two variables, so I'm just going in circles, right? So what I really want is I want to be able to add these x's or add these y's such that the same thing will happen that happened to my 11 and my negative 11. I want it to go to 0. Because if it goes to 0, then I have eliminated one of the variables. Does that make sense? So I'm going to rewrite this guy. 3x plus 5y equals negative 11. That was one of my x minus 2y equals positive 11. I know that if I add them together right now, I'm not going to get anywhere. So, somebody who knows what they're talking about here, what change can I make before I do this addition? Go ahead, Katie.
Multiply the second by 3 or negative 3.
She's saying multiply equation 2 by negative 3. Is that legal? As long as I do it to both the left and the right, that's perfectly legal, right? So what happens if I take the left-hand side times negative 3, and I take the right-hand side times negative 3? That's legal. Okay? Now I'm going to rewrite this equation. I'm going to distribute minus 3x plus 6y equals negative 33. I've created a new equation, but I know that that equation is true because I did a legal maneuver to get it, right? Why did Katie choose negative 3? Because the x's are going to cancel out when I go back up to rewrite my number 1, right? So let's write this one right underneath it. I'll rewrite number 1. So now I have two true equations. And now notice what's going to happen when I add all my left-hand side together and all my right-hand side together. The negative 3x and the 3x, that gives me 0x, which is just 0, which is nothing, so I can forget about it, right? They eliminate each other. That's why it's called the elimination method. And then over here I have 11y, and over here I have negative 44. Now I can solve for y. This is easy. Y is equal to negative 4. And now I want to figure out what x is. Keep in mind that every one of these equations is legit. They're all true. They're all true statements. So whichever equation I choose to plug my x back into, it doesn't matter, because all of them should give me the exact same answer. So I'll just go back up and I'll plug it into my my original. I'll plug it into my original right here, which was x minus 2y equals 11. So if x minus 2y equals 11 and y is negative 4, I'm going to get x plus 8 equals 11. So x must be equal to 3. Anybody with me? 3 and negative 4 as my two answers. Not too bad. So, did you not get that? Did I screw up?
I don't know. I got negative 4 and 19.
Somebody help me out. You got the 3? I bet you got 19 because you ended up with a negative 8 here and it should have been a positive 8? Yes?
I guess.
Did you put negative 4 there or positive 4?
Yeah, I put negative 4.
Is it you have a negative 2 there?
Well, I just did the x minus the 2 times the negative 4. I didn't add the negative sign onto the 2.
So, negative 2, negative 4 is positive 8.
Yeah, I didn't do negative 2. I did positive 2 times the negative 4, and I took x minus that answer.
Ah.
And I forgot the negative.
Order of operations, right?
Yeah.
Yep. Well, it still would have, yeah.
Yeah.
Yeah, I see what you did. Yep. Okay. So which way is easier? Substitution? The elimination? I think what you'll find if you did enough of these practice-wise, some of them are going to lend themselves to substitution, namely the ones where it's really easy to get x or y by himself. Like this one, it's pretty easy to get y by himself. You can do it in one easy step, and then substitution seems to make sense. But this one, again, this one would have been pretty easy to get x by himself. One step, move it over, and I could have got x by himself. And then substitution works pretty good. The ones where substitution is a little dicier would be like if I gave you something like this, negative 13x plus 49y equals 118. And 29x minus 7y equals 12. Now substitution looks like a pain in the butt, right? Because I'm going to deal with fractions and all kinds of stuff. Now I contrived this one off the top of my head very quickly. Why would elimination work better here? Why is it faster and easier?
Multiply 7 to 49.
Yeah. Do you guys see the y's? One's 49 and one's a negative 7. There's a quick maneuver I could do to make those cancel. What would I want to do? I'd want to take the bottom equation, both left and right, times who? Positive 7. Because if I did that, notice how this would distribute. When I go 7 times negative 7y, I'm going to get negative 49y, which happens to match up perfectly with my positive 49y, and they're going to cancel for me, right? If I would have made this like 51 instead, then it would have still involved fractions and ugliness, right? So there's the elimination, there's the substitution, and finally, let's talk how we can have our computer help us. What happens if I took, well, let's just take this ugly one that I just gave you. I'm going to rewrite it. I don't have this on the PowerPoint. minus 13x plus 49y equals 118. And then 29x minus 7y equals 12. There's the guy we're interested in tackling in the box there. And you're feeling lazy. You don't want to substitute. You don't want to eliminate. But we have this wonderful tool right at our fingertips, right? We can maybe graph it on our calculator or our computer and see what it spits out. If I were to graph equation number 1 here, this top equation, what shape is it going to make? That should be easy, by the way. Can you guys identify the shape? What happens if you got y all by himself? Y equals mx plus b? It's going to be a straight line. There's no exponents here. There's no absolute value. There's no square roots. Nothing like that. It's just a straight line, right? Go to your computer. Type in negative 13x plus 49y equals 118. Okay, I'm going to make my font size a little bigger here. Okay, I am typing in negative 13x plus 49y equals 118. Enter. Notice that it gives it, I told you it was going to be a straight line. Should be right up here. If you want to view it in y equals mx plus b form, you can always right click on it and go y equals mx plus b, and now you can see the slope and the y-intercept if you prefer to see it in that method. Okay? The other one I'm going to type in is 29x minus 7y equals 12. That was the other one I had written down. Enter. Again, if you want to see it in y equals mx plus b form, you can. But what are we interested in here? The intersection. We're interested in the x and the y value that satisfy both equations. If you just look at one equation, there's an infinite number of x and y combinations that go on that one equation because the line goes forever. So it's like saying how many points are on this line. Well, there's an infinite number of points on that line. And if I go to my second one and I say how many points are on that line, there's an infinite number of points on that line. You can't solve one equation if it has two variables. Does that make sense? Because there's an infinite number of solutions. But if I have two equations and two variables, then most likely, if they're lines, there's going to be one unique solution. There can only be one because lines never turn around and come back, right? Now, if I did a line, let's say this was one of my lines. If I did a line and my other equation was like a quadratic, well, that's different. How many solutions does that guy have? Well, one there and one there. Two different solutions would work for that guy. But if you have a line and a line, is there any way that they can cross more than once? No, they can only cross once. Or they could be the exact same line and lay right on top of each other. If that was the case, you'd have an infinite number of solutions, right? What's the third possibility? They either cross once, they lay right on top of each other, or they're parallel. They never cross at all. What happens if they were parallel? If this one goes right here, and this one goes right here, and they never cross each other. Is there going to be a solution of an xy that satisfies both? No, there's no solution. So you're either going to get infinite number of solutions if they lay right on top of each other, no solutions if they never cross each other at all, but more often than not, the case is going to be that they're going to cross one time and exactly one time. Okay, how do I figure out the point where those two cross on my computer? I'm going to do a new point and I'm going to do an intersect. Remember that friend of ours? Intersect point right here. So I choose that and then I go over and I click on my two lines. I click on one of them, I click on the other one, and it spits out my answer in decimal form. if I changed my my rounding, notice that these look like these are going to be decimals that go on forever. So my answer is going to be like some kind of fraction, but they're going to intersect at that point. So, graphing, fairly easy. Yes, I hope so. If you know how to use your computer or your graphing calculator, I mean, you can do the same thing. For those of you that have a graphing calculator, you can do the same thing on here. Let me have you try a couple application problems, and then we'll get out of here today. I don't care how you solve it. Go ahead and do it via substitution. Go ahead and do it via elimination. Go ahead and graph it. But try to solve that problem. Let me know when you have an answer. I'd like to check it out. Very nice. Very nice. How'd you do that, Katie? Paper, pencil?
Yeah.
Okay. Very nice. I'm assuming that's your adults and that's your children? Yep. Very nice. Very nice. Did you get the same thing?
Yeah.
What do you got? Anything? Now, the difference between this one and the other ones that we did is that they're not just coming out and giving you the equations, right? If they just said, hey, here's two equations, solve this system, that would be different. This one is requiring you to come up with your own equations. So, we know that we have adults and we know that we have children. So there's our two variables, right? Like I called mine A and C. Then I can remember which one is adults and which one is children. You can call it X and Y if you want. The only danger in that is which one was adults and which ones was kids. I don't have that problem because I use A and C. See how clever that is? So, what are my equations? Whether I used X and Y, A and C, whatever, one of my equations is that on a certain day the attendance is $2,000 or 2,000 people. So A plus C is equal to 2,000. Does that make sense? If I add the children and I add the adults together, it equals 2,000 total humans. That's one of my equations. The other one is talking about money. After these 2,000 people came through the gate, we collected $70,000. Well, we don't know yet. Was it 2,000 adults and 0 children? Was it 1,000 adults and 1,000 children? Like, you could guess and check your way and figure it out, but that would take absolutely forever. So we don't want to guess and check. We just want to use a little bit of simple math to help us here. So what can I do then? Instead of guessing and checking, I could say I already know one of my equations is going to be this guy right here. The total number of people is 2,000. I also know that we're charging $25 for children, so $25 times every child, and $50 times every adult. That's my total revenue, and that should be equal to $70,000. Now I have two equations with two variables. Now I can do my substitution, or my elimination, or my graphing. It doesn't matter. I did substitution because this A and C looks like a really easy guy to substitute. So I said A was equal to that. I plugged in 2,000 minus C into my second equation. And then once I've done that, the algebra is pretty easy once you've got it set up, right? 1,200 kids, 800 adults. One more item for you guys to try. Last one. Our goal is to get home as fast as possible. Okay? Get home as fast as possible. So we got to choose. Do we choose the subway or do we take the bus? That's our choice. Okay? Which vehicle is faster? Bus or subway? Faster speed? The subway. Because the subway, in 3 minutes, it can go 2 miles. Whereas the bus, in 3 minutes, it can only go 1 mile. So the subway speed is twice as fast as the bus. You guys catch that part? But what's the trade-off here?
It starts months later.
It starts later. Yeah, the bus, I can get on the bus right away when school is over. Even though it's a slower moving vehicle, it starts right away. It gets a head start, if you will, right? Whereas the subway, I'm going to have to sit around and wait for 7 minutes before I can even get on it. See what's going on here? I want you then, so a little kid walks out of city center school and says, "Hi, should I take the bus or should I take the subway?" You need to give that kid advice. And I can tell you right now, the answer is not take the bus or take the subway. That's not good enough. You need to give a better answer than that. See what you can come up with. This is the type of problem I would expect you to be able to work through. was a little tougher than I thought. That took me a while. Anybody got it? What are we actually interested in? We want to minimize the time it takes to get to home. Do you guys agree that at some point, the bus is going to get a head start, right? At some point, the subway is going to catch up? The question is, where is that point where the subway catches up? It's like if I'm fast and Alex is slow. If Alex is fast and I'm slow, and we're going to have a foot race, he's going to give me a head start, correct? But eventually he's going to pass me. If we can find that point where the subway catches the bus, that will determine what advice we can give to the kid, right? What do we need to know from this kid before we give him or her advice?
How far you live.
Yeah, where do you live? Because if you tell me how far away you live, then I can tell you which vehicle to take, right? Did anybody solve it? I know we're out of time here. Anybody? What'd you get?
We said if you live farther than 4 2/3 miles, you should take the subway.
Yeah, 4 2/3 is what I ended up with. Let me just show you quick how I did it. We got a minute left. Depending on if you were doing distance or time or how you were setting up your variable, I said that distance, the bus can go 1/3 of a mile every minute, and the subway can go 2/3 of a mile every minute, but I got to subtract 7 minutes off, right?
Yeah.
If I went with 7 minutes, I'd still be at 0. So the subway's not going to make any headway until minute number 8. Okay? That was kind of, you didn't have to set it up the way I did it, but maybe you did it differently. I don't know.
We just said 3x equal to 1.5x plus 2.
Yeah, much simpler. Yeah, that was way better. This would have been another one where I would have said, you know what? I'm pulling out my computer, and I'm going to graph it and see. But anyways, you end up with the distance being 4 2/3 miles. So if you live closer than 4 2/3 miles, take the bus. If you live further than 4 2/3 mile, take the subway. And if you live right at 4 2/3 mile, it doesn't matter because they're going to be there at the same time, right? Okay, I will be here at 12:30 on Friday for anybody who wants to start their test early. See you then.
Was that not funny?